This is bonding page 1. Since ionization requires energy, we've been looking at that, about how much energy it takes to remove an electron. You might wonder, why would ionic compounds ever form since electrons have to be removed to form ions? So this introduces a new concept called lattice energy. The exothermic component of an ionic bond is the lattice energy, and it's the lattice energy which is the change in the enthalpy. So this is another delta H, just notice the subscript lattice, released when gaseous ions, so that's a really key thing, is that you have gaseous ions here, and they are coalescing into a crystalline solid. So, key thing here. So lattice energy is determined by means of what's called a Born-Haber cycle, a series of steps from elements to ionic compounds for which all the enthalpies are known except for the lattice energy. And this is really just a Hess's law, so you'd have to be given lots and lots of data to do this. So this requires you to know lots of definitions. So sublimation of sodium is sodium going from solid to gas, and again, that's because this has to be gaseous. So you'll see heat of sublimation here, and again, that is endothermic, so you'll see it's positive. Breaking the covalent bond in the chlorine molecule, so chlorine is generally diatomic, so we have to split that. So you'll see that this is a bond. Okay, and we'll get to this little asterisk in a minute. Ionization of sodium is removing that electron. Again, you'll sometimes see this as first ionization energy, so we could probably add that here as first. And so ionization 1 is the notation here. The electron affinity of chlorine, so chlorine's going to attract that electron to itself. Notice that's also negative. And then the formation of NaCl. So remember, heat of formations are the element in their normal state, half of Cl2 to get your NaCl. So I wrote this equation for lattice out. So I have sodium ions as a gas, chlorine ions as a gas, yielding sodium chloride as a solid. So if you're looking at all of these things that we have here, we need to look at which ones we're going to have to flip. So formation of NaCl, so this one is in the correct order. The electron affinity is going to have to be reversed because we need the Cl minus. So I've got to reverse that, so I'm just going to put parentheses around the reversal. The ionization energy I also need reversed, so we're going to get those reversed to be negatives. I have to have this one to cancel this one. So the 239 is also going to reverse. And you'll notice there's a little asterisk here. This is 2 of them. I need 1 of them, so we're going to take a half of that and also reverse it. And this NaS is a solid here, so to cancel this NaCl Cl solid, I have to reverse that one as well, which also helps me cancel this one. So you'll see almost all of them have to be reversed to get them in the format we need to be able to cancel. So you'll see them all combined down here. So the negative 412 minus the reverse of all of these, 109 plus 239 divided by 2, that's the half, plus the 495, and negative 349. So if you put all of those together, that's going to give us negative 787 kilojoules per mole, which is going to give us an overall negative value exothermic. That is the lattice energy for this compound. And again, it's spontaneous because products are lower than reactants. So we're going to look at some trends in lattice energy. So the effective ionic size. So it goes exactly what we were just doing with periodic properties. As you move down a group, the ion size is going to increase. And therefore the distance between the ions would decrease. and therefore your lattice energy would decrease as well. And of course, this trend assumes that you're having the same ion charge for both the cation and the anion. The second piece of this is the effective ionic charge. So the higher the charge, the greater the lattice energy would be. So think of, again, Coulomb's law. If I increase the charge, that increases my attraction greater. And we see the same thing here with lattice energy.